Hi folks, we're going to look at our sum and difference identities as well as our half angle, double angle, and power reduction formulas. Your reading has the derivation of all of these formulas. It starts with the sum formula for cosine and uses that to derive the rest of them, both the sum and difference formulas and the half angle and double angle formulas are all derived from that first kind of geometric argument for the cosine sum formula. And if you'd like a separate video on that, I can do a separate video going through all of those derivations. But for these notes, we're going to go through using these tools. For those of you going on to calculus and the associated physics and engineering and even some of the chemistry, these tools become fairly common manipulation tools that we have to use for some of our calculus work and some of our engineering work. Historically, they were used to determine values of functions for other values other than just our standard angles. If you want to find the sine, cosine, tangent, whatever of a weird angle, you build it out of angles that we knew using these sum, difference, double, and half formulas. Nowadays, we don't tend to use them for that because we have computers and calculators and whatnot that we can, or even just tables that we can use to determine the values without having to do that. But these remain important tools because they're really important manipulation tools, particularly in integration once you get to Calc 2. Calc 2 students, even sometimes in Calc 1, but especially in Calc 2, there are sections in which I hear a lot of students say, man, I wish I would have paid more attention when we did the identities in trig. So do try to focus some on these tools if that's where you're going. And even if that's not where you're going, they're still useful manipulation tools. For us in here, because we aren't doing those higher end things with them, we will be doing a lot of evaluating to try to find exact values of more obscure angles, because that's what we can do with them so far. But once you get there later on, you'll see that these become important manipulation tools. So these are formulas that you'll have on some of your notes, but you do want to try to memorize as much of them as you can. I certainly don't recommend that you try to memorize a double angle formula for cotangent, for example. Nobody does that. But trying to keep some of the structures in mind, like what they look like and how they're built, can be really handy, especially if all it's doing is making you think, hey, wait, isn't there a formula for that? I think there's a formula for that, and you go look it up. That can often be enough. So, but particularly when we get to the double angle formulas, and some of the power reduction formulas, there are a couple that I'll point out that are really helpful to know just because they come up so often. But let's look at using them. So if we look at this first example, this example is asking us what the sine of 75 degrees is. And as I said, we could grab a calculator that has scientific functions on it and ask it what the sine of 75 degrees is, and it will give us a decimal approximation, and a pretty good one. But if we wanted to get an exact value as a way to practice these manipulations, if we can build 75 degrees out of angles that we know, then we can use these sum and difference formulas to combine those into finding out what the sine of 75 degrees is. Now, that will, for a while seem fairly restrictive, but once you have the sine of 75 degrees, then if you have something else that you're looking for that is, say, I don't know, 105 degrees, if you know 75 degrees now and you know 30 degrees, well, 30 plus 75 is 105. So you could do angles based on angles that you derive and eventually combine to make just about anything you want. And that, again, is an old-fashioned way of using these tools to find values before we had computers. But again, we're practicing it more as a manipulation tool. Now, it might be tempting to imagine, hey, couldn't we just take the sine of 45 degrees and add that to the sine of 30 degrees? That would be nice, but unfortunately, it's not true. You know, it's similar to the idea that if you have, say, x plus 2 quantity squared, it's tempting to think, hey, can we make that x squared plus 2 squared? But eventually we learn that that doesn't work, that exponents don't distribute over addition like that. That instead we have to multiply this out and use FOIL or equivalent tools to get its expansion. Really, one of there are very few times when we can distribute something along addition like that. It just happens to come up a lot, so it turns into something that feels like it's reasonable. Multiplication can distribute that way, sure, but almost nothing else can. Like if you have the square root of x squared plus 9, you can't turn that into x plus 3, no matter how nice that seems like it would be. So it's tempting to think, hey, can we just take the sine of those pieces and put them together, add those results, but it doesn't work. What does work are these tools. And again, those derivations are in your text where these tools come from. But once we have those derivations, if we want to know what the sine of a sum is, well, it's going to be the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. So grabbing that formula, this has to equal the sine of 45 degrees times the cosine of 30 degrees plus the cosine of 45 degrees times the sine of 30 degrees, according to this relationship. Now that's a lot more pieces, but it's pieces that we know. So we've turned the sine of something we don't know into the sine and cosine of things that we do know. And grabbing your unit circle, we know the sine of 45 degrees is the square root of 2 over 2. The cosine of 30 degrees is the square root of 3 over 2. The cosine of 45 degrees is also the square root of 2 over 2. And the sine of 30 degrees is 1/2. So we can then bring all those pieces together to say that we've got the square root of 6 over 4 plus the square root of 2 over 4. It's nice to have common denominators there. So the square root of 6 plus the square root of 2 over 4. And it might seem strange, but that's our exact answer. We can't do any more simplifying than that. I mean, if you really wanted to, I guess you could write that as the square root of 2 times the square root of 3 plus 1 over 4. But I don't know if that's better in any way. So it does seem strange to stop there, but that's an exact value. So that's really how we're going to use these tools. Now, we're not always going to be told how to break up the 75, and there are a lot of choices. We didn't have to do 45 and 30. We could have done any combination of the angles that we know to build 75. For example, if we jump up here, we want to find the exact value of this cosine of 7 pi over 12. Well, I don't know anything about pi over 12s. I know about pi over 3s, I know about pi over 4s, pi over 2s, pi over 6s. So we'd have to break this up into something that's got pi over 4s, pi over 3s, the pi over 6s, the ones that we know. And we're going to do that by breaking this up either into a sum or a difference. It doesn't matter because we have a formula for each. And it's going to be some number of pi over 12s, either plus or minus some other number of pi over 12s, such that those add to make the 7 pi over 12, and such that they will both reduce into things we know, things we like, pi over 4s, pi over 3s, pi over 6s. So, for example, if we put a 2 there and a 5 there, well, 2 pi over 12 plus 5 pi over 12 would turn into 7 pi over 12. And 2 pi over 12 would reduce to pi over 6, and we know about pi over 6, so that would be handy. But 5 pi over 12 doesn't reduce. So while it's true that that turns into 7 pi over 12, it's not actually helpful. So we want to think about not only adding to that 7, but in a way that would be helpful. But they could subtract too, so we could have, hey, you want to subtract them? We could have 9 pi over 12 minus 2 pi over 12. That would reduce. 9 pi over 12 would reduce to pi over 4s. 2 pi over 12 would also reduce. It would reduce to pi over 6s. So that should work. Are there other combinations that would work? Absolutely. But let's try this one. So that's going to turn into the cosine of 3 pi over 4 minus pi over 6 when those reduce. And we know about pi over 4s, we know about pi over 6s. So all we need to do is grab our relationships and look at what do we do about the cosine of a difference. So the cosine of a difference has its own expansion. Cosine of A, cosine of B, so the cosine of the first one, cosine of 3 pi over 4 times the cosine of pi over 6 plus, do be careful about that, notice the signs switch with cosine, so plus the sine of 3 pi over 4, just a sine of the first one, times the cosine of pi over 6. And again, the idea is we know what each one of those are. Cosine of 3 pi over 4 is negative square root of 2 over 2, looking at your unit circle. Cosine of pi over 6 is square root of 3 over 2. Plus sine of 3 pi over 4 is positive square root of 2 over 2, because we're up in quadrant 2. Cosine of pi over 6, square root of 3 over 2. So we get negative square root of 6 over 4 plus, that was supposed to be sine, wasn't it? Sine. Yeah, it started to not look right. Sorry. Cosine, cosine, sine, sine for the cosine formulas. So it is still plus, but the sine of 3 pi over 4 and the sine of pi over 6. So that times 1/2. So negative square root of 6 over 4 plus the square root of 2 over 4 And I might be tempted to write this as the square root of 2 minus the square root of 6, just so I don't have that negative out in front, over 4, and that's our answer. Now that might look a lot like the answer for the other problem, except there's a negative instead of a positive, and the 6 instead of the 3 and whatnot. And it should look similar, because we're building it out of the same pieces. We're building it out of pi over 4s, pi over 6s, pi over 3s, and those standard angles that we know. So it's going to be built out of square root of 3 over 2, square root of 2 over 2s, halves, and so on. So don't be surprised when we end up with a lot of answers that look fairly similar. They're made out of the same building blocks, so that shouldn't surprise us too much. Now, some of you might be bothered by the idea that, well, why didn't we break it into, say, 4 pi over 12 plus 3 pi over 12, because that would have also made 7 pi over 12. And we totally could have. And it would have worked out. That 4 pi over 12 would reduce to pi over 3, one of our standards. And the 3 pi over 12 would reduce to pi over 4, one of our standards. And, they're even nice, comparatively. There's no pieces over in quadrant 2. Those are both nicely in quadrant 1. The big difference is we'd be using the sum formula instead of the difference formula, so we'd be up here. But that's okay. Cosine A, cosine B. So cosine of the first one times the cosine of the second one minus, again, remember the sign changes with cosine, sine pi over 3 times the sine of pi over 4. Again, now we've turned it into something in terms of angles we know. Cosine of pi over 3 is 1/2. Cosine of pi over 4 is the square root of 2 over 2. Minus sine of pi over 3 is the square root of 3 over 2. Sine of pi over 4 is the square root of 2 over 2. Again, from your unit circle. So we get the square root of 2 over 4 minus the square root of 6 over 4. Again, common denominators occur naturally. So the square root of 2 minus the square root of 6 over 4. Which is the same answer, of course, that we've got down here. And frankly, a little bit nicer, because we were in, just quadrant 1 angles. But either way works. You just have to find something that both adds to what you want and reduces. When you're dealing with degrees instead of radians like we did down here, we don't have to worry so much about reducing. We just have to worry about building it out of the pieces that we know. So that's nice. When you're dealing with the trig functions, because you have, when you're dealing with radians, because you have usually fractions that you have to build, that you have to kind of undo the common denominators that built what you have. So that's a little bit trickier. But if you can try this idea of just splitting it up, oh, that's fun. I can pick up the numbers. Just splitting it up into 2 pieces and going, okay, what numbers can I put there that will add or subtract to make what I want, and also reduce to things I know, then you can nicely build something that's going to work. And that's fun. Okay. So, given that the sine of alpha is 4/5 and the cosine of beta is negative 1/4 with A and B in quadrant 2, evaluate this difference. Now this might look a little bit nasty, but the nice thing is it's really built from the things we've already been doing. A and B, or alpha and beta, are in quadrant 2, so for alpha, we're somewhere here in quadrant 2, such that that length is 4 and this length is 5, because we are y over r. So a little Pythagorean theorem will tell you that this side has to be negative 3. So we've got to go figure that out before we do much else. And we also know that beta is in quadrant 2 because we're told that. So we're some angle here in quadrant 2 for beta, such that the cosine is -1/4, so x over r. So again, a little Pythagorean theorem will give us this side, which I think will be what, the square root of 15? Yeah, because it'll be a squared plus b squared equals c squared, where that's the hypotenuse. So -1 squared, if you want, plus b squared equals 4 squared. So b squared plus 1 equals 16. So b squared equals the 15. So b is plus or minus the square root of 15. And because we're in quadrant 2, we need that y length to be positive. So we choose the positive value. And we've done that a bunch. Just thought we'd run through it and make sure my 15 was correct. So once we have those two pieces, we'll be able to build not only the sine of alpha, but we'll know what the cosine of alpha is. Not only do we know the cosine of beta from this diagram, we know what the sine of beta is, and even the tangent of beta, or the cotangent of beta, if we wanted to. So once we have those pieces, we go, okay, so we want to evaluate the cosine of the difference between these two angles. And I don't care what the angles are, and I don't care what the difference of the angles are. Notice I haven't gone to any trouble to try to calculate what these angles might be. We don't have to. We know what their sine and cosine is, so we can evaluate what this is. Looking back at our formulas, we see that the cosine of a minus b is the cosine of, well, alpha times the cosine of beta plus the sine of alpha times the sine of beta. Again, cosine subtractions turns into addition. With a sine, the sine is preserved. So the cosine of alpha, well, we can get from our diagram. The cosine of beta, we were told, is -1/4. The sine of alpha, we were told, 4/5. The sine of beta, we can get from our diagram. So the cosine of alpha has to be x over r. That's why I had to figure out that -3. So -3/5. And the sine of beta, sine's got to be y over r, so square root of 15 over 4. So square root of 15 over 4. So how about 3/20 plus 4 square root of 15/20? Again, common denominators. That's going to happen naturally for many, if not all, of these problems. Notice we could reduce this 4 and 20 if we wanted to, but don't reduce it. You want the common denominators. So if you have common denominators, leave it alone. And we end up with 3 plus 4 square root of 15 over 20, and that's done. We can't reduce the 4 and the 20 there because it doesn't go into that 3, so that's just a nice exact answer. So the trick here is essentially, when we need that cosine of alpha, it's like, well, we don't know the cosine of alpha, we only know the sine of alpha. But we've got practice. If we know the sine or cosine or tangent or whatever for an angle, we can find all the other 6 trigonometric functions. You've had a lot of problems like that. This is one of the reasons we practice that skill, is because then when we know something about those pieces, we can turn that into finding out what we can know about their combinations. That's for a double angle formula. We haven't gotten to double angle formulas yet. All right, let's make sure that's the right number 3. Oh, it's not, that's why. Oh. Where's my other number 3? looks the same. Oh well, we'll do it that way. So this is jumping the gun just a tad in some ways, but in other ways it's not. But it does show you kind of an example of where this comes from. But given that the tangent of some angle is negative 3/4 and it's in quadrant 4, that should immediately set you off into finding a diagram. If you've been told that you have this trigonometric function in this location, that means this has to be happening. The y over x, so 3 and 4, and one of them has to be negative to get the negative, and quadrant 4 tells us that the y is the negative. So this information tells us this scenario. A little Pythagorean theorem will get you that r value of 5. And that's what we're going to use to try to figure out what the sine of 2 theta is. Now, as I said, we haven't done the double angle formulas yet, but we don't actually have to, because the double angle formula is really just a sum. 2 theta is just theta plus theta. So even without deriving the double angle formula, though this is how one derives the double angle formula, we can still just use our sum formula to find out what the sine of 2 theta is, as long as we know what the sine and cosine of theta are. Now, we weren't told the sine and cosine of theta, but because we were told enough information to make this diagram, we'll be able to figure out what the sine and cosine are. So, we look back at our formulas, we see the sine of a plus b is the sine of a times the cosine of b plus the cosine of a times the sine of b. And again, that's on page 1. So that's the sine of alpha times the cosine of alpha plus the cosine of alpha, because they're both alphas. Sine of alpha, which, yes, you could make 2 sine alpha cosine alpha, because you've got 2 of them, and that is our double angle formula for sine. But the sine of alpha, if we want to keep them separate, we know the sine of alpha because we have this diagram. The sine of alpha has to be y over r, so negative 3/5. Cosine has to be x over r, so 4/5. Plus the cosine of theta, it's the same theta, so 4/5. And the sine of theta, it's the same theta, so negative 3/5. So negative 12/25 plus negative 12/25 is negative 24/25. And that's the sine of 2 theta. Now, this is a nice exercise to do because it does build, hey, these match because the angles matched. So couldn't we have just done 2 sine theta cosine theta? And yes, we could have. And as soon as we get to our double and half angle formulas, which we will in a minute here, that's what we'll do. We'll go directly to that. This is one of the handiest of our identities, by the way. It comes up a lot. Okay. So, establishing identities, again, that means we're just going to manipulate one side to try to build the other, just like we did last week. And this is part of what I meant about this being, in a lot of ways, a manipulation tool, not just an evaluation tool. So just like we did last week, we're going to pick whatever side looks uglier or looks like it's got more complication and then try to simplify it down to make the other side. So I'm certainly going to start on this side. And I don't necessarily know exactly how to approach this, but I do know what the cosine of alpha plus beta can turn into. Looking back at our formulas, the cosine of alpha plus beta is the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. That's what the cosine of alpha plus beta can turn into. And then the cosine of alpha minus beta, so this is one big plus, the cosine of alpha minus beta turns into the cosine of alpha times the cosine of beta. Again, the negative here turns into a plus here, the sine of alpha sine of beta. Now, I don't know why that might help, but that's what these two statements, these two little sub-expressions can open up into. And then we look and see, hey, did anything helpful happen? Just like we did with our problems last week. And lo and behold, something helpful did happen. Notice we have negative sine alpha sine beta here and positive sine alpha sine beta there. So those are going to subtract and turn into a 0, leaving us with cosine alpha cosine beta plus the other cosine alpha cosine beta. And the sines all subtracted away. And this is the same thing added to itself, so that's two of them, 2 cosine alpha cosine beta, which is what we were supposed to show. So good, we verified that identity. The big thing is not to get stuck going, I don't know what to do with this. Well, we know that this equals something else, so write that out. We know this equals something else, so write that out. And then look and see what happens. When we're verifying or establishing identities, that's what we want to do. Just manipulate it how we can, trying to build or find that piece that makes things simplify. Okay. Now we also have, we have these nice angle sum and difference formulas that we've been talking about. But we also have these double angle formulas, and we actually saw up there how the double angle formula for sine is built. The other double angle formulas are really built the same way. These are all simplifications of cosine alpha plus alpha and tangent alpha plus alpha. The reason there are a bunch of variations of cosine of 2 alpha, the double angle formula for cosine, is just because, notice both of these have squared trigonometric functions, which means they can be manipulated with the Pythagorean identities. So if you change this cosine squared out with 1 minus sine squared, then you're going to have 2 sine squareds there. If you change this sine squared into 1 minus cosine squared, you're going to get 2 cosine squareds. So it's just the fact that you can use the Pythagorean identity to manipulate this statement means you can write it a bunch of different ways, depending on what you know and depending on what's handy. So the double angle formulas are fairly easy to derive. And frankly, if you solve these double angle formulas, you get these power reduction formulas. Solve this for sine squared, and you'll get the power reduction formula for sine squared. And then take the square root of both sides, and you get the half angle formulas. And again, this half angle formula is a little bit ugly, but you might remember these are conjugate pairs. We talked about conjugate pairs last week for simplifying identities. So if you multiply by the conjugates, you can build more simplified forms for the tangent. That are just handier to use. So the derivations of these, it's a lot of derivations, and it's a lot of writing out how to build them all, but they come fairly naturally from those sum and difference formulas. And the nice thing is, no one's going to ask you to derive them. What we're going to ask you to do is be able to use them. So we want to see some examples of using some of these tools. So, for example, okay, you might notice this does look a lot like the example we did before. The only difference is here we're just going to go directly to the idea that, hey, the sine of 2 alpha is 2 sine alpha, oh sorry, sine theta cosine theta from our double angle formula for sine. And this is one of the big ones, by the way. I mentioned it up there, but this, because it's sine times cosine turning into something, this identity comes up a lot in calculus, in engineering, in lots of places. So if you're going to straight up memorize and remember forever one of these, this is the one to know, just flat out, if you have to pick one. The sum and difference formulas for sine and cosine are also nice to know. Some of the double angle formulas for cosine are nice to know, but this one for sine, double angle formula for sine, if you're going to memorize one, memorize this one. Not only is it one of the most useful, but it's also one of the simpler ones. So anyway, so we can turn this sine of 2 theta into 2 sine theta cosine theta based on our double angle identity, but we still need to know what sine theta and cosine theta are, and that's why we'll need that diagram and why we need to be told that it's in quadrant 4. Because if we don't know that it's in quadrant 4, we don't know which one of these is negative and which one of these is positive. So because we're in quadrant 4, we know that's a -3, that's a +4, and a little Pythagorean theorem will build that 5. But then we get 2 times the sine of theta, and the sine over here has to be the -3/5, -3/5. Cosine of theta, x over r, so +4/5. And we get 2 times -12/25, which turns into -24/25. Same thing it did before. Okay, this question, I think that what's difficult about this next one is just like trying to figure out what it's asking you to do. It's asking us to use double angle formulas to write the cosine of 6x in terms of the cosine of 3x. So using double angle formula means we have to make some sort of argument based on our double angle formula. So we know that the double angle formula for cosine says that the cosine of 2 times something equals, well, we've got a bunch of options. We have one that's just, oops, that's not those. Let me move those formulas over so we can look at them. We've got one that's in terms of sine and cosine. We have one that's in terms of sine, and we have one that's in terms of just cosine. Okay, it's cosine squared, but still, it's only a cosine argument. So we're going to grab that and say that cosine of twice something is equal to 2 times the cosine squared of that something minus 1. Well, 6 theta, or 6x, is twice 3x. So if we think of 6x as the cosine of 2 times 3x, then that's equal to 2 times the cosine squared of 3x minus 1, according to our third double angle formula for cosine. So, recognizing that, that means the cosine of 6x is just equal to 2 times cosine squared of 3x minus 1, and that's an expression entirely in terms of the cosine of 3x. Now, if we want it to be in terms of sine of 3x, we could have used this one that just has sine. If we want it to be in terms of sine and cosine, we could have used that one. More often than not, we end up using one of these two because they're of some inherent advantage in the problem of being just sine or just cosine. So yeah, this question can be a little bit hard to read in terms of what do they want, but that's what they want. Okay, a little half-angle formula action happening down here. So as I said, we have these power reduction formulas, which we won't use a lot here, but we will use it more in calculus, particularly calculus 2. Those power reduction formulas, or just reduction formulas, come up quite a lot. So they are good to be aware of. That's one of those ones where, isn't there a formula for that? Yeah. Go look it up. You're not going to memorize those. You might memorize a couple of them eventually when you're in calculus, but you're not going to do it now, and that's okay. So, we're asked to find the cosine of theta over 2, given that we know the sine of theta, and we're in, that's again, quadrant 4. So again, anytime you're told information like this, you should really draw that diagram so you can see what it's trying to tell you. That means we've got a negative square root of 5 over 3 for our y over r. So a little Pythagorean theorem will give us that other side if we want it. And since our half-angle formula for cosine is a cosine argument, just knowing the sine's not going to be good enough. We need to know what that other slide length is so we can talk about cosine. So a little Pythagorean theorem, again, a squared plus b squared equals, that's not b, square root of 5. Let me rewrite that. A squared, whatever that a squared is, plus negative square root of 5 squared equals 3 squared. So a squared plus 5, negatives undo each other, square undoes the square root, equals 9. So a squared equals 4. So a equals plus or minus the square root of 4, or 2. Because we're in quadrant 4, we know that that's a positive 2. If we were in quadrant 3, it would be the negative 2. Again, that's one of the reasons we want to remember that plus or minus. So, that tells us that the cosine of theta is 2/3. It also tells us that the tangent of theta is the negative square root of 5 over 2, but we don't need to know that. We know, because we can build that diagram, we know all of the other 5 trig functions, whichever ones we need. But since the cosine of theta over 2, is either plus or minus, we'll talk about that in a second, the square root of 1 plus the cosine of the angle on top, that alpha is that alpha, so that theta is that theta, over 2, so it's either plus or minus the square root of 1 plus the cosine of theta, which we've already said is 2/3, over 2, and we need to simplify that. We'll do that in a second. But we have to determine whether this is going to be positive or negative. And we have to be really careful here. Because we might look at this and say, hey, we're in quadrant 4, and this is a cosine argument. Cosine's positive in quadrant 4. But that's not the angle we're looking at. We're looking at theta over 2. So the question isn't, where is theta? Theta is certainly in quadrant 4. The question is, where is theta over 2? So if we take this 3 pi over 2 less than theta less than 2 pi and transform it into an argument about theta over 2, divide everything by 2. This is saying theta over 2 has to be between 3 pi over 4 and pi. And we divided 3 pi over 2 by 2, so it turns into 3 pi over 4. So the argument of this cosine is between 3 pi over 4 and pi. Well, that's quadrant 2. So theta is happening in quadrant 4, but theta over 2 is happening in quadrant 2. And cosine in quadrant 2 is negative. So we have to use the negative here. Be very careful about that. It's not the quadrant where the original information is coming from. It's the quadrant for the argument that we're making. And we have to determine which one of those, whether it's the plus or the minus, based on the quadrant we're in. So that means this is going to be negative the square root of 1 plus 2/3 over 2. And you certainly shouldn't leave it like that. Nobody wants fractions in their fractions. And the best way to get rid of fractions in your fractions, particularly not fractions in your radicals, but the best way to get rid of fractions in your fractions is to multiply by whatever your denominator that you want to get rid of is. So I want to get rid of that 3, so I'm going to multiply top and bottom by 3. So that's going to give us negative the square root of 3 plus 2 over 6, or the square root of 5/6. And if we're going to rationalize that, which is a good habit, it's going to be the square root of 30 over 6 when rationalized. You multiply by that. You turn this into the square root of 5 over the square root of 6. Multiply by the square root of 6 over the square root of 6. So those go away. That turns into 30. So for the most part, you're still just, well, what do I know about theta over 2? Well, I know theta over 2. I know the cosine of theta over 2 turns into this thing. So we just plug it into that thing. But we still have to go figure out what our cosine value is. And we have to determine whether we're using the positive version or the negative version. This only really happens with the half-angle formulas. The other ones kind of take care of themselves. And even tangent, notice these other variations of tangent don't have the plus or minus in front of it. That's because that manipulation solves that issue. The manipulations required to get these alternate forms solves that issue. So it's only these 3 where you have to figure out what your sign has to be. But be careful, don't leave both. It's not 2 answers. It's a function, only allowed 1 answer. You have to determine whether it's the positive or the negative by determining what quadrant you're in. All right. For example, how's my time doing? 48, getting a little bit long, but we'll try to finish it up. So find the exact value of the cosine of negative 3 pi over 8. It's like, well, I don't know anything about 3 pi over 8. I know about 3 pi over 4. I know about 3 pi over 3. So I need to try to turn this into something that I know about. Well, as I said, I know about 3 pi over 4. And 8s are half of 4s. Fourths, anyway. So 3 pi over 8 is 3 pi over 4 divided by 2. So I can look at this as my theta, and you might prove to yourself that that does, if you perform that division, you get negative 3 pi over 8. So that makes that 3 pi over 4 our theta. Thus, this is going to equal either plus or minus, and we'll figure out which one in a second, the square root of 1 plus the cosine of that theta, negative 3 pi over 4. We'll have to figure out what that is in a second. Over 2. Now, is it positive or is it negative? Well, again, negative 3 pi over 4 is in quadrant 2, and cosine's a negative in quadrant 2. But that's not the question we're asking. We're asking for the cosine of negative 3 pi over 8. And negative 3 pi over 8 is in quadrant 4. 3 pi over 8, 3/8 is less than a half. That's less than pi over 2. So it hasn't gotten out of quadrant 4 yet. So this is a positive. That can take some getting used to. If it helps, draw it out. 3 pi over 8, well, if that's pi over 2, then that's pi over 4, pi over 2, it's negative pi over 2. That's negative pi over 4, that's negative pi over 8, half of that, so 1, 2, 3 pi over 8's, negative 3 pi over 8, that's solidly in quadrant 4 still. And cosine's positive in quadrant 4, so this thing's positive. Okay, what's the cosine of negative 3 pi over 4? Again, we turned this into a 3 pi over 4 argument because we know about 3 pi over 4s. Cosine of negative 3 pi over 4 is negative square root of 2 over 2. All over 2. We could turn that into 1 minus the square root of 2 over 2 all over 2, just to get rid of those parentheses. But then again, I've got fractions in my fractions, which you can imagine it's going to happen a lot with these. Again, going to fix it the same way we fixed it up here. Up here we fixed it by multiplying by 3 because our denominator had a 3 that we wanted to get rid of. Here, we don't want to get rid of a 3. We want to get rid of this denominator of 2. So, we're going to multiply by 2. We're just multiplying by whatever that denominator we want to get rid of is. So that's going to turn into the square root of 2 minus the square root of 2 over 4. Or the square root of 2 minus the square root of 2 all over 2 if you square root that denominator. Now that's ugly, a square root in my square root. I hate when that happens, but sometimes we have to deal with that happening. And it actually happens a fair amount with half-angle formulas, unfortunately. Okay. My card is starting to get a little overwhelmed, so I'll try to get through these fast, but not too fast. So use the diagram to evaluate the expressions. Well, again, the nice thing would be to finish off the diagram, so do a little Pythagorean theorem, get that side's 13. Because we're in a triangle, all of our arguments are going to be positive, so we don't have to worry about the plus or minus aspect of it. So sine of theta over 2, well, again, we grab our formulas. So the sine of theta over 2 is going to be positive because these are all acute angles, so they're all going to be in essentially quadrant 1 angles. 1 minus the cosine of alpha over 2 And the cosine of alpha, this is alpha, so it's adjacent over hypotenuse. So 1 minus 5/13 over 2. And we're going to clean that up the same way. Multiply by the denominator we want to get rid of, so multiply by 13. And we're going to get the square root of 13 minus 5 over 26. Or the square root of, what's 13 minus 5? 8 over 26. Which will reduce to 4/13. And then I'm going to multiply by the square root of 13 to rationalize. Square root of 52 over 13. I know that rationalization happened fast, but that's your simplified version. Half-angle formula for cosine. Notice both the sine and cosine, the half-angle formula is based on a cosine argument. That's because they're both built from double-angle formulas for cosine being solved. Essentially, you solve this one, you get the sine. You solve that one, you get the cosine. And they're both cosine arguments. That's why both of these are cosine arguments, in case you're curious. The main difference is, instead of 1 minus, the cosine argument is 1 plus the cosine of alpha over 2. But the cosine of alpha is still 5/13 over 2. So I'm still going to multiply by 13. And you could get common denominators and work that out if you wanted to, but I think it's easier to do it this way once you're practiced with it. So 13 plus 5 this time over 26, things square root. So 18/26 square root, which that will reduce to 9/13 square root. Oh, that's nice. So 3 over the square root of 13, which is going to turn into 3 square root of 13 over 13. I know that's fast, but go back and watch it and slow it down. Once you have the tool, it's just simplifying it. All the trig happens here. Really, all the trig happens here. Just applying that formula. The rest of it is just simplifying. Tangent, I'd probably tend to use this version of tangent just because, I don't know. I don't have it just because, for no reason. This one would be just as nice. This one's more annoying. But either one of those, I'm going to use this first one just because. So it's the sine of alpha over 1 plus the cosine of alpha. The sine of alpha would be opposite over hypotenuse, so 12/13 over 1 plus the 5/13. And again, you could get common denominators and stuff down here, but just, you have a denominator you don't like, multiply by it. That would be 12 over 13 plus, 13's cancel here when it distributes, so plus 5. So 12/18. Divide both of those by 6, and you get 2/3. 2/3. And again, I know I'm rushing through those, but really all the trig is going, hey, this turns into that, and we know those pieces. The rest of it's just simplification. I'm starting to hit that hour too, so I want to get you guys out of here and get my graphics card from getting too full. We got these 2 left. Just do those real quick. So evaluate 5 pi over 4 using 2 different approaches. Well, we could just grab our unit circle and say, hey, 5 pi over 4, that's pi over 4, 2, 3, 4, 5 pi over 4 is down here. So at 5 pi over 4, we're at negative square root of 2 over 2. and negative square root of 2 over 2, so the cosine of 5 pi over 4 is just negative square root of 2 over 2. So that would be, one nice direct way. But we could also turn this into any number of combinations of things other things that we know. We could say this is the cosine of 5 pi over 2 over 2 and use a half angle formula if we wanted to. That's one option. It's probably not the best option, but it is an option. We could turn this into the cosine of 3 pi over 4 plus 2 pi over 4 if we wanted to. That's probably a nice option. Yeah, I like that option. Let's do that option. That one's nice because this reduces to just 1 pi over 2. So that's going to reduce to pi over 2. And then our angle sum formula for cosine says this is the cosine of 3 pi over 4 times the cosine of pi over 2 plus turns into a minus the sine of 3 pi over 4 times the sine of pi over 2. And again, you just look at your formulas and just decide that. Now the cosine of, 3 pi over 4 is this square root of 2 over 2. It's negative because we're in quadrant 2 there. Cosine of pi over 2, though, is 0, so that whole thing's going to go away. Minus sine of the square root of, sine of 3 pi over 4 is positive square root of 2 over 2. And sine of pi over 2, look at your unit circle, is 1. So it's just the square root of 2 over 2 again. But any way of breaking this up into a sum, a difference, a half, a double would also work. And the key there is just knowing that you have options. Figure out which option seems most reasonable, and then break it into those pieces. So it's a little bit of a creative process, and that can sometimes throw people off because they want to know, what am I supposed to do with this problem? And there really isn't a supposed to do. It's what can you do and play with it. And what's wrong with just using 5 pi over 4? Nothing at all. But then can you approach it in some other way? Stretch what you think you can do. Establishing identities. So again, we're going to grab what we know we can turn tangent of something over 2, so our half angle formula for tangent. And, we don't have a half angle formula for cotangent, but we'll kind of fix that. Where'd my cursor go? But I want to grab, while I still have ability to move stuff around, grab those. The big thing is we just have to decide which version of the tangent half angle formula we want to use. Yeah, this is going to get a little clippy. But I'm certainly going to use, I'm going to use this one because this one has a sign in the denominator and we're trying to get a cosecant, so that makes me think of signs in denominators, so I'm going to use that. Is that the best thing to do? I don't know. Let's find out. Tangent of x over 2, so that's going to be the sine of x over, I said I was going to use this one. Let me stick with what I say. 1 minus the cosine of x over the sine of x plus, now the cotangent is the reciprocal of tangent. Well, that means it's just going to be the reciprocal of these tangent half angle formulas. So if you want, that's 1 over the tangent of x over 2. So it's going to be 1 over whatever these are. So it's just going to be the reciprocal of these tangent arguments. So for this tangent argument, I'm going to use the other half-angle formula for tangent so I can get both of them in the denominators. That's tricky. So then that's going to be the 1 plus cosine x over sine x, because we're using the reciprocal of that one. Now, notice when you add those together, the cosines subtract away, and 1 plus 1 is 2 over sine x. Well, 2 over sine x is 2 times the cosecant x. So this one, I think, really comes down to very strategic use of which ones you're picking based on the goal that we had. Because we knew we wanted cosecants, putting those signs, making sure those signs were in our denominators, made that really helpful. Okay, a little over an hour, but we got both our note sets in, so I think that's really handy. Again, if you want a video on the derivation of these tools, it's a lot of manipulation, but it can be good to see. I'm going to email either to me or whoever your current instructor is, and they should be able to set you up with that. And have a beautiful day.